Hi, everyone. Welcome to this session on incorporating AI in your applications. I'm JR Gauthier. I'm a product manager and a data scientist. I worked on the OCI data science service, and I'm with my colleague Priyana Hassan. Priyana, would you mind introducing yourself a little bit?
Hey folks, how are you doing today? My name is Priyana Hassan, and I am a principal member here of technical staff on the Oracle Kubernetes Engine. And previously, I also worked with JR on the Oracle Data Science Service.
That's right. Yeah, we're pals working on the same service for a while. All right, so let's move on into the actual presentation. All right, so we're going to be making some, we're going to be talking about features that are in our roadmaps. And so we are including this safe harbor statement into our presentation. So just you're aware of this. All right, so what you will learn in this session, so you will learn how to train and deploy predictive machine learning models as containers that can be later consumed by applications. So you learn about the design principles that are driving the support for machine learning use cases on OCI. You'll see a demo where we're going to build, train, and deploy a machine learning model on OCI using GPUs. And then you'll find some resources on how to build and deploy those machine learning models on OCI yourself. Priyana, would you mind walking us through a little bit of the different steps we're going to go through in this demo?
It would be my pleasure. So, like JR said, you're going to be learning about how to leverage GPUs on OCI to deploy a deep learning model. And what I'm going to show you here is just a few of the technologies and tools that we're going to be using to do that. So first of all, you're going to be training your model using a tool, a framework called TensorFlow that lets you train neural networks in something called the JupyterLab Notebook. That's going to be done through the OCI Data Science Service. And then we're going to package your model up into a Docker container, and we're going to push it to something called a Docker registry. From that registry, we're going to deploy it to Kubernetes Engine, and we're also going to deploy it using the OCI Model Deployment Service. That is going to use GPU nodes using NVIDIA GPUs. And then finally, once those models are deployable, we have to be able to route to them, and we're going to be routing to them using a combination of two tools, one of which is called the Seldon Inference Framework, which is a component of Kubeflow, and Istio, which is a service mesh for routing.
And I just want to point out that as you'll see in the demo, using GPUs is actually going to make your model training a lot faster than using CPUs. It varies on the use case by use case, and it depends on the complexity on the model and the size of the data set that you're using. But you can train up you can speed up your training by anywhere from 50% all the way to, I've seen, up to 10 times faster on GPUs than CPUs. All right, so what you're going to see in the demo is really an end-to-end kind of model lifecycle demo. We're going to be using two services to do that: OCI Data Science and OKE. So the first step we're going to do is train a model on a GPU in the OCI Data Science service. We're going to use notebook sessions to do that. As Priyana mentioned, we're going to take that model. It's a TensorFlow model. We're going to export it, and we're going to deploy it through OKE. The model is going to be wrapped in a container, and we're going to use Seldon to do that. And the model is going to be exposed as a REST API endpoint. What I will show you in the second half of this demo is how you can essentially do these steps using the OCI Data Science service. So we're going to build, train the model in the notebook session. So we're going to start from there. And then I'm going to take the model. I'm going to prepare a model artifact that I'm going to then save into the model catalog. And once it's available in the catalog, I'll be able to deploy it as an HTTP endpoint. So it's going to be a similar path, except that in this case, the model server is running not in a container like you would in OKE, but it's running in a VM. And then we're using con environments to package the dependencies that your model need to run. So this is a little bit different because in the case of OKE, you're going to build a full-blown Docker image. In the case of model deployment in OCI Data Science, we're really just leveraging the con environments themselves. All right, so let's see a demo.
Thanks, JR. So first, we're going to get started with a demo that deploys a TensorFlow model to an OKE cluster. And then after that, JR is going to walk you through deploying the same model using the OCI Model Deployment Service. So now we're going to look at training a TensorFlow model within a data science notebook. In here, I have the data science notebook that I've already created, and I've loaded in a training script. This is a very, very simple model that's using TensorFlows, and we're training a simple Keras sequential model, just consisting of a few layers. First things first, we're going to show that we are indeed using the right GPU drivers. So you'll see that we have a number of GPUs available. And then we're going to bring in our data set. We're going to do a little bit of very basic pre-processing. And then we're going to add some layers to our neural network. Then we're going to print out a summary of our model that shows what all of our layers are. After that, we're going to actually train the model. So we're compiling it here. We've specified a loss function. And now we're going to fit the model. And this is what training is. This is going to take just a few moments. Once it's finished, we'll be able to evaluate our model using our test data set. And you can see here that our model has 97% accuracy. That's pretty good. So we'll save our model. And our model now should have been saved in here. And you can see that it was just modified. So that means it was saved. Now, if you wanted to export this model, you could. I would suggest that you create a tar file and then download that tar file and build an image with it. And I'll show you how to do that in just a minute. But before we do that, we're going to go ahead and take a look at our model. The code that you see here is basically the same code template that we're going to be packaging up into a Docker container and then deploying within Kubernetes. So you see that there's a my model object here. There's a predict function. And this is dictated by the Selden IO framework. Selden likes to have a predict function that looks like this with this signature. We accept an input. We do some processing of it, and then we return our prediction. So let's try it out. We're going to load in our same test data set, and we're going to process it the same way. And then let's go ahead and try to predict a digit. So I'm going to choose the second element in our test data set, and it looks like our model thinks that it's very, very likely that the number in this image is the second element in the array. So it looks like our model thinks that the number is 1. We'll find out. It was indeed 1. And we can try this again, maybe with a different image. This time, it looks like our model is really certain that the number is a 0. So let's see. Well, would you look at that? It's a 0. So now that we're done here, I'm going to show you in just a moment how to deploy this to Kubernetes. Let's go ahead and take a look and see what that looks like. Over here, I have a pre-created Kubernetes cluster. And I'm just going to very quickly walk you through what it looks like to create a Kubernetes cluster. Like I mentioned before, we have a quick create option that's pretty straightforward and pretty easy to use. This quick create option actually goes and creates all of the resources that you need to get your cluster up and running for you. So if I go to launch workflow here, it'll take us to a screen, and you can choose the kinds of nodes you want. You can choose how many of them you want. And we also have some advanced options here, like adding an SSH key in case you want to debug your node, or just SSH in to install anything, any drivers or any data that you might want. You can also specify a custom boot volume size. It's all pretty straightforward. I'm going to cancel this though, because we already have a little cluster up and running. And so once you get your cluster up and running, it's really, really easy to get access to it. All you have to do is copy this handy command that we provide for you and pull down your kube config, and that's basically it. You can start kubectling and interacting with your cluster. Now, I've taken this image and I pushed it to something called the OCI Container Registry. And in doing that, I went ahead and was able to deploy it as a pod within Kubernetes. And I'll show you just what that looks like right now. So here I have a pod, and it has kind of a funny name, and you're going to see just why. This is a pod that was created by Selden. This isn't a pod that I created manually. It's part of something called a Selden deployment. So if we look a little bit more closely at this pod, you'll notice that it has a number of annotations, and this is so that Selden can track it. So Selden creates this pod, and it's running an image, which is this GPU demo, basically just the code that we created. And Selden goes ahead and adds all these annotations. I definitely did not add these annotations manually, but I will show you in a minute just how that works. So first of all, though, before we do anything more, let me show you exactly how Selden does that. So you see here that I have a model, and it has a type called Selden deployment. And that's a custom type that Selden knows how to interact with. And how do you deploy and define a Selden deployment? Well, it's just like this. It's really simple. So there's this little YAML file here. There's not a whole lot inside of here. There's just the specification. I'm using a private Docker registry and repository, which we recommend that you always do. And so I have to specify an image pull secret. Then I have the actual image itself, and I want this to be scheduled onto an NVIDIA GPU host. So I'm definitely going to say that I want NVIDIA GPUs. And then Selden basically does the rest. It ingests this, and it creates a container, creates a pod, basically. Kubernetes creates the container and hooks everything up so that you can actually hit it. And you're probably wondering, well, how did all of this stuff even get put into an image? Well, there's actually a really nice tool that exists, and it's called S2I, and that's basically source. It basically takes your source code and packages it up into a container. And so the way that it works is like this. You just type in this command and you say what you want the container name to be. And then it's going to go ahead, look inside this GPU model package, and build everything that I want. It's pretty smart. So it knows how to build it. And you're probably wondering, well, how does it know that? Well, there is a little file here. And it basically is able to use that specification file to tell me what it wants. So this is all that's in that specification file. It's called an environment file, and I just say what I want my model name to be, what kind of API it is, what the service type is, and whether I need any persistence, and I don't. So that's all there is to it. There's not too much more. This is going to take a little while because it's going to download all of TensorFlow and create my model image. It's not super fast. So in the meanwhile, though, while this is happening, we're going to go ahead and try to interact with this model. So we're going to set up port forwarding. Remember, I have a service over here that Selden has set up for me in front of my model very, very conveniently. And so you can see it's right there. It's happily sitting. And I'm just going to go ahead and try to hit my model here. And you see that it went and it talks to my model. So this handled the connection. And we can do it again. And we should see that connection handled again. And then we have a different result. And remember, these match up, right? So image number 2 was the first image that we did was a 1, and that's what it says right here. And then the second image we did was a 0. And so that's it. That's basically all there is to it. You can see on this right-hand side that it's still building this image. This takes a little while. It takes about 6 minutes in total. These images are pretty big because they have quite a lot of dependencies. So it's around 5 gigs, which is, pretty darn large. That concludes our demo of deploying a TensorFlow model on an OCI cluster using the Selden inference framework. Now, back to JR.
So as you saw in Priyana's demo, we were able to train a TensorFlow model. So I'm just back in the notebook session here. And what I'm going to do is I'm going to prepare a model artifact with that TensorFlow model. I'm going to save it into the model catalog in the OCI data science service. And then I'm going to deploy that as an HTTP endpoint through the model deployment feature. So the first thing that I need to do is import the ADS library. So there's an ADS call here being made. ADS stands for Accelerated Data Science. It's an ASDK that is part of our notebook session environment. You can also access it in the content environments that we provide as part of the service. So ADS includes a whole bunch of functions and toolkits on manipulating models and model artifacts. So I'm going to be using this to prepare my artifact. So the first thing I need to do is create a local temporary folder. I call this MD test artifact, where I'm going to, that's going to host actually the artifact object itself locally. So the second step after I've created that local folder is to call the prepare generate model function in ADS. So what this does is it creates 2 files in my artifact folder. It creates a score.py file and a runtime.yaml. Score.py is the contract definition that model deployment is going to use to load the model object to memory and make a prediction on a sample data. And then runtime.yaml actually provides a reference to the content environment that I want to use for inference purposes. This is the content environment that model deployment is going to use to capture all of the dependencies that the model needs to run. So once I've prepared my model artifacts, I'm just going to execute this. The next step is just to save my model object. So in this case, it's a TensorFlow Keras model. So it's an HDF5 file format. So I'm going to save this in my artifact folder here in my notebook session. So pretty straightforward. So what I'm going to do next is modify the score.py file. So this is my contract definition. I'm modifying 2 functions. There's load model. What I'm going to do here is essentially just take the load model function that you can find in TensorFlow Keras to load that H5 file in memory. So load model just return that output object here. And then I'm going to modify the predict function. What the predict function takes is a sample data. It's in the JSON format. It's loading this to memory, converting it to a NumPy array. And then I'm going to use that NumPy array, convert that into a tensor to be able to make a prediction. And so what my model is returning here is a set of predictions, predicting the classes, the most likely class for each sample payload. So I'm going to modify score.py. And so I'm writing this in my artifact folder. One thing that I always like to do is test my score.py before I save my model. It's always good practice to make sure that you test your contract. So what I'm doing here is very simple. Is from the artifact folder, I just load the score module, score.py module, and I'm going to import the load model and predict functions. And I'm making a sample call to it. So I'm taking the first 3 images of my training data set. I'm converting them into a JSON string object, and then I'm calling the predict function in my score.py file. And I'm expecting to see some predictions stored in the predictions underscore test variable here. So let's take a look. So my model predicts the values of 5, 0, and 4, and those should match the payloads that I passed to my model here. So the first 3 entries in my training data set. So I see 5, 0, and 4. So we're in good shape. All right. So the next step, once I'm satisfied with my model artifact, is to save that model into the catalog. So what I'm doing here is I'm leveraging the save method from that artifact object, and I'm taking the model and saving it to the catalog. So I'm giving it a name called MNIST model2, and I'm giving it a description. So I'm just going to execute this, and it's going to create a new entry in the model catalog. So I'm getting the model OCID back here. So this is all done through ADS. I'm going to go to the console here and look at the new model entry. So I can just pick one of the model entries. This is a new one that I created. If I click on one of them, you can see we capture a whole bunch of information along with the model. So more than just the model artifact, we capture the training resource. So we have a bunch of provenance information about the model itself, what notebook session was used to train the model. We also capture model taxonomy metadata. So the use case, the framework, the version, the algorithm that was used, the hyperparameters of that algorithm also are captured. Custom attributes like the loss, the accuracy of the model, as well as a reference to the CON environment that was used to train the model. So I use a CPU, GPU environment here. So it's captured as part of the metadata as well. So once the model is in the model catalog, you can take a simple action here and create a model deployment. So you can do it through the console, but I'm going to go back to my notebook and I'm going to show you how you can do that programmatically. And we're going to use ADS to do that. So let me go back to my notebook. So the first thing you may want to do is import ADS. ADS has deployment module here, and there's a few objects you may want to import like model deploy, model deployment, and model deployment properties. The first thing you want to do when you deploy a model is create a model deployment properties object. And so this object will capture all of the parameters of your deployment. So the first thing is specifying a model OCID. So this is the model that I just created. You want to give it a name to your deployment, assign a project OCID, a compartment OCID. So I'm choosing the same project in the same compartment as my running notebook session. And then you assign a compute configuration. So in this case, I want to run my model server on only one instance of type standard 2.1, and I'm going to assign a load balancer bandwidth of 10 megabit per second. So if you execute this, you create a model deployment properties object, and then I simply have to call model deployer, create a model deployment instance, and pass the properties. And this is going to create a model deployment object for me. So it takes a few minutes typically to create a model deployment, but I've already created one for this demo. So we're just going to go back to the console and just take a look at what that looks like. So once you create a model, you can go back, model deployment, you can go back to the projects page and look under model deployments. Once the model deployment is good and ready to go, it's in an active state. And you can access some of the resources associated with your deployment. Probably one of the most useful one is going to be under invoking your model. If I click here, you can see the model HTTP endpoint. So this is the endpoint that you will want to call later on to make predictions. You can copy this URL here and then use it in your notebook in a Python script. You can use the OCI CLI, the Python SDK, or the Java SDK to actually call that endpoint. So I'm going to go back to my notebook session because we're going to use ADS to make a call. So I'm using the predict endpoint, and then we're going to use again the same 3 images that we used previously to test the score.py file. So as you see here, the same predictions were returned, about 169 milliseconds for the endpoint to return the predictions. You can do the same thing if you want. So I'm using ADS here. You can use OCI SDK to make that call. You just have to paste the URI in your notebook session. You can use either resource principals to authenticate to that endpoint, to that model endpoint, or you can also use user principal if you prefer to do that using the config and PEM file. So just create the signer you need, and then simply use post call to using the request library with your input data in JSON format. You can use other type of MIME types if your model endpoints support that as well. So in this case, it's a very simple use case. Small images, 28 by 28 pixels. So a JSON payload is perfectly fine. And so that really covers the story here. So you can build, train your models inside of a notebook session. You can prepare an artifact using ADS, save that artifact in the model catalog, and then from there, you can either deploy to the console or programmatically, as we saw in the notebook, a model as a model deployment object. So that's it for me. Let's go back to the presentation. So I'm going to talk a little bit about the OCI data science service you saw in the demo. We offer a few different tools in the service, one of which you saw was notebook sessions. We offer JupyterLab as an interface to build and train your machine learning models. It's a fully managed experience, so you don't have to worry about provisioning, patching, the underlying infrastructure. We take care of that for you. We support a variety of VM shapes, both for CPUs and GPUs. So we support Intel, AMD, the flexible AMD shapes as well. We support NVIDIA, the older generation of P100 GPUs, the V100, as well as the upcoming A100s in a few months. We'll support them as well. We also have persistent storage for your data, your notebook, and your content environments that you can attach to the notebook sessions themselves. I think we support up to 10 terabytes of storage per notebook session. This is a great feature because you can pause your notebook session. We're going to keep everything that you've created in that block volume drive. And so while the notebook session is paused, you're not being billed for it. And then you can later resume, or what we call activate, your notebook session. And we're going to reattach that block volume to your notebook session, and then you can resume your work. So this is a great feature that our customers love. We offer Git integration, so you can pull your notebooks and your files from third-party version control, a remote version control provider of your choice, whether it's GitHub.com or Bitbucket or GitLab. We have an integration with OCI Vault to manage your secrets and your credentials, so you don't have to write your username and your passwords in your notebook. So you can just simply connect to the Vault and pull those credentials securely in your notebook. And then the pricing model is very simple. You really only pay for the infrastructure that you consume. So in this case for notebook session, you only pay for the VM itself and the block volume that you attach to it. So there is no overhead, no tax on top of this. So the service is essentially free to use. You can use your favorite open source tools on the platform. We have a variety of open source tools, including TensorFlow that you saw in the demo. They're packaged in different content environments. If the tool that you need or the version that you need is not available in one of those content environments, you can always create your own conda, and you can then install the libraries of your choice. And as far as model deployment is concerned, this is, again, a fully managed experience. So you can build, train your models in your notebook session, prepare an artifact, store it in the catalog, and then deploy that as an HTTP endpoint. It's all managed. It's a very streamlined experience. So once the model is in the catalog, it's a single step really to deploy those models. You can do it to the console. You can do it programmatically through the various OCI SDKs, ADS, and the CLI. It's fully managed again. So you just have to pick the VMs that are going to be running the model server, the number of them that you want, as well as the load balancer bandwidth. And then any calls to logging, the Python logging library in your score.py file, any call or any printout to standard out or standard error can be redirected to the OCI logging service. So this is one of the integrations that we offer, as well as part of model deployment. So you can, if you capture your input feature vector, so the data payload itself, to the logging service, and if you capture also the model prediction to the logging service, you can start building your own model drift analysis by looking at how the feature distributions are changing over time, or how the model predictions are changing over time. All right, I'll pass the mic to Priyana.
Thank you, JR. So I'm going to talk to you a little bit about our container engine for Kubernetes. We like to call it OKE. The full name is OCI Container Engine for Kubernetes. It is a fully managed service that is basically upstream Kubernetes, but we've done quite a few things to simplify operations beyond what upstream Kubernetes offers. So the first things first, as you saw in the demo, cluster creation is really quite fast and quite simple. So rather than having to go through and configure your cluster manually, you basically can use the CLI as you saw in the demo, or you can use the console, and we go ahead, create your cluster for you, set up all of your networking, set up access to your cluster, and provide you with some very simple instructions to pull down your kubeconfig and begin interacting with the Kubernetes API right away. Not only that, but we offer a number of security features that improves the security posture of your cluster. So we make sure that every single image is attested. You can enable this, which essentially means that the images that you are using within your applications are verified. So their provenance is verified. We know exactly what source they're coming from and we trust that source. Not only that, but we offer a number of high performance shapes that are available through OCI Compute, including GPUs, which again, you saw in the demo. So all of these things combined make OKE a pretty easy to use and robust platform for Kubernetes. And so now we're just going to go ahead and quickly recap what we walked through. So you saw quite a few things. And I think what we really want you to take away from here is the steps that we walk through in this demo reflect some important design principles for production model deployment. So these are tools that you should be using to have reliable deployments of your models, which are reproducible and are traceable. So one of the things that we did is we used JupyterLab, which is an open source notebook framework. We used TensorFlow, which is an open source model training framework. And we used Kubernetes, which is an open source containerized deployment and application framework. We built our apps as services. So we built our models as services that are able to communicate through APIs. And what that does for us is that actually allows us to, create models that are distributed, for example. And it allows us to manage these models as stateless applications. So you might have 1 or 3 or 5 or 1,000 replicas of your model, depending on the volume of traffic or the volume of data that you're trying to score. So imagine that you have an e-commerce website and you want to provide recommendations for a user. You want to be able to easily scale these models out to be able to provide recommendations no matter what your load is. So that's really important. The other thing you saw us do is you saw us package and ship these models as containers. Every container has a unique SHA. So just like when you make a commit in a Git repo and you have a unique identifier for that commit, every single image has a unique identifier. So you know exactly what image your model corresponds to, what version of your model corresponds to. And finally, you saw that we use fully managed services to reduce a lot of the complexity around model deployment and application management. So for JR and I, who've been working in the space for a long time, we remember back in the day when this was pretty hard. You would code up a model and it would be really hard to figure out how to deploy it. There were entire teams of individuals who worked to help data scientists deploy their models. And that's not the case anymore. With these tools that you saw us use, data scientists, engineers, analysts are empowered to train their own models and deploy them themselves, sometimes with just one click.
Yeah, absolutely. There's been quite a change in the landscape in the last few years. Data scientists are now empowered to deploy their models almost by themselves these days. A few resources if you want to learn more about our services. For OCI Data Science, we have our blog. You can also access our YouTube playlist where we show different screencasts, demos, and tutorials. And you can also access our public GitHub repo where we include sample notebooks, scripts, and general best practices on how to use the service.
You can learn more about cloud native on Oracle Cloud Infrastructure, and that includes Oracle's Container Engine for Kubernetes, That includes container registry, functions as a service, all of those tools that we use to deploy models on OCI. And also, if you're more interested in using Kubeflow with OKE and want to learn how to get started, we have a blog post on that as well.
So, all right, we're now ready for the Q&A portion of this presentation. So let's take a look at some of the questions that we have in the chat. All right, so the first question that we have is, does OCI data science support R models? So I know the presentation was very Python centric. So we use TensorFlow, we use a lot of the Python tools. Our condos were all centered on Python open source libraries. So the service right now does not support R models. It's in our roadmap actually to support R models, but it doesn't at the moment. Let's see if we have any other questions. There's another one here. Can you use your own conda environments for inference in model deployment? Yes, you can. By default, we have about 18 or 19 conda environments that come pre-built in the data science service. You can use those as the runtime environment of your model deployments, but you can also create your own. So we provide the tooling in the notebook session, for example, to build those condas. It's the ODSC CLI that you can use to build those condas. Once a conda is built, it's available in your notebook session, and then you can, what we call it, publish it. By publishing a conda, what it means is that we essentially take your conda environments into your notebook session, and we zip it and we ship it to an object storage bucket that you own. So it's an object storage bucket in your tenancy. Once it is available in your tenancy, you can then use it. You can put a reference to it in your runtime.yaml file in your model artifact, and model deployment is going to pull that conda environment out of your object storage bucket and use it as the runtime environment of your model. So absolutely, yes, you can build your own condas for building, training your models, and then you can use them also for inference purposes.
So it looks like somebody has asked, does OKE support other model deployment frameworks? Yeah, so you don't have to use Selden like we did in the demo. You can use basically any of the Kubeflow framework. So you can use TensorFlow serving if you wanted to, for example. You're not limited. If you go through and go to the blog post that we linked that shows you how to get Kubeflow up and running on OKE, you can use any of those tools on OKE. And yeah, you can also, set up Istio, or you can use Ambassador like we did in the demo to actually do your routing and have sort of more complex routing between your models. We have another question. Can you access models that are deployed on Kubernetes Engine from your corporate network on premises? Yes, definitely. So OCI has a network tool that is called Fast Connect. And what you can do is you can set up a network connection from your data center directly to OCI. And through that Fast Connect virtual cloud network, you are able to access your Kubernetes cluster as usual, as though you were, basically in a regular network. So once that connectivity is established, it's not a problem. And we have a number of guides that actually walk you through how to establish a Fast Connect. And just to build on that a little bit, on Oracle Kubernetes Engine, your manager instances, your entire Kubernetes control plane, that is a completely private cluster. So nobody outside of your virtual cloud network will be able to access that by default. So it's secure by default. You can modify the connectivity preferences as you wish. Obviously, we advise everyone to keep that control plane completely private when possible. But yeah, so you're already sort of in your own network with your cluster just out of the gate.
Thank you so much for being here. Thank you, Priyana. I hope you learn a lot of good tools and tips on how to build, train, deploy your machine learning models on OCI using OKE and the OCI Data Science Service. Thank you.